tables that guests can use to order and pay. And I believe we are actually the second largest public-facing deployment of iPads in the country, at about 15,000 now, second only to Apple itself in the Apple stores. And then prior to OTG, I was the tech guy at a data analytics startup called Potentiometrics, and that's where I started using Ansible. I think it was version 1.6 at the time. And for me, back then, it wasn't preference, it was necessity. I was the only person doing the tech side of things there. Ansible really acted as like a force multiplier, letting me manage a lot more stuff than I would have been able to just on my own. And the biggest challenge for me getting started with Ansible was the gap between general introductions, best practices, those kind of things, and specific examples of how to use certain modules or deep dives. I had a lot of questions about how to do things like managing configuration data or associating the SSH keys with particular servers, or when to split up task files. The 500 different questions you realize you have when you start actually using a tool. So my goal for this talk is to give you something that you can go home and try out for yourself. The code and slides and all this are on GitHub. Links to that later on. Answers I found to these sorts of questions over the years of working with Ansible. And something that's also complex enough to have real-life usefulness. So everything I'll be showing you is from a setup I actually use on a daily basis, with some minor adaptations such as getting it to run in AWS. So we have a number of different physical locations, different terminals, and for the most part, our backend systems are separate. So Terminal A and Terminal B have their own database server, their own API services, and so on. And generally speaking, our apps are location agnostic. They point to generic local domains that then resolve to the local instance of that particular resource. And then additionally, many of the resources have a global domain name that can be used to directly access the system regardless of the location you're at. So because of this, our internal DNS system is a really critical part of our infrastructure, even more so than it would be for most companies. For example, if we have a DNS server go down, that's a problem, but it's better than a situation where we have a DNS server that's up, but handing out the wrong addresses. In that kind of a situation, we could very easily have an app that looks like it's working, but it's actually sending data to a totally different location. So prior to this project, our DNS system was one of a couple of things running in these largely undocumented black box servers that nobody really understood. Changes were difficult to make, and a lot of times they didn't quite do what you expected them to do. And we were also working on a new set of testing environments around this time, and we were just having a lot of difficulty getting these new testing environments to play well with our DNS servers. So we decided it was finally time to build out a new DNS system. So we're going to be rebuilding a core part of our infrastructure. We want to make really sure we don't repeat the same problems that got us to the current point. So what got us there? Well, first, we didn't really know what these DNS servers were supposed to be doing. We didn't have a formal or even an informal set of requirements. We had a few examples of how things could break, but we didn't really have a clear definition of what it meant for one of these servers to be fully functional. For example, what are the list of domains these systems should be resolving? And then along those lines, we had a rough sense of what the architecture was supposed to be. But some of the pieces of the original design hadn't been fully implemented. The terminal level DNS servers were intended, we think, to automatically pull zone data for the global zone from our central DNS server at our corporate office here in Manhattan. But at least some of them were actually using hard-coded local copies of that data instead. The biggest contributor to our issues, though, was configuration drift. The original DNS servers were, as far as we know, configured fully by hand, manually built out, and then they've been changed and tweaked over time. So we had significant differences between the servers at different locations, and a lot of them were doing a bunch of other things, such as running NTP, various monitoring tools, and in at least one case, unused instances of both MySQL and Postgres on the DNS server. So once these new servers are built, how do we make sure we keep them clean and we prevent this configuration drift from happening again? Well, every once in a while, we're going to blow them up.
Yeehaw.
So this is where the Phoenix server concept comes in. So back in 2012, Martin Fowler wrote a short article describing this concept of Phoenix servers, saying, it's a good idea to virtually burn down your servers at regular intervals. A server should be like a phoenix, regularly rising from the ashes. Also, in case you're wondering at this point, this is not related to the Phoenix project, so sorry to disappoint there if that's what you came looking for. At least not directly related. Okay, so Phoenix servers sound great, but how do we get there? So first step is going to be developing a definition of what the system is actually supposed to be doing, and then codifying those requirements into testing, or test cases. Once that's done, we'll set up a baseline environment that includes the standard utilities used by all of our servers, including any dependencies we have for Ansible. And then from there, we'll use Ansible to incrementally build out the system, getting these tests to pass one by one. So our team's motto is we fail a little better each time, and that's exactly what we're going to do in this step. So fail a few less tests each time. And then finally, we're going to burn down these servers fairly often, both to keep them clean and to confirm that the playbooks we're running are actually doing what they're supposed to be doing. Okay, so first step, defining what the system is supposed to be doing. So as is often the case with legacy systems, we came into this not really knowing what these systems were supposed to do. So we used a mix of human and technical sources to develop a rough list of requirements, including talking with our developers, talking with our IT team, examining application code, and then actually just digging through network traffic and doing packet captures and things like that. The result was an incomplete list of requirements, but that's all right. Like, we can add additional functionality as we realize it's required later on. And then finally, we took those requirements and we started converting them to things we can actually measure and test. So Nagios checks and other things that can be baked into our monitoring system. Ansible tasks, which come back to that in a couple slides, and then details on more manual or complex tasks like loading a menu, ordering an item, doing a card swipe, paying for it, that kind of stuff. So after going through this process, we were able to put together a rough set of requirements. So first off, the core functionality. From our background research, we were able to put together a fairly complete list of domains that need to be covered. This includes a handful of these local or generic domains that had to resolve to different addresses at each terminal. We also have a set of domains in this global zone that are going to resolve the same way everywhere. And then a handful of other zones that need to be forwarded to other systems. So our AD servers or just open DNS for everything else. And additionally, this thing there, we learned about several local domain names that need to be resolvable at some locations, but not others. So we need to do some level of conditional logic based on whether, say, a location uses an inventory system from a particular vendor that requires certain domains. Okay, so the second piece, we want the DNS server, the local DNS servers to handle that local zone, and then defer to the central DNS server for the global zone. That's the central server at our corporate office. There's a complication to this, though. So as I was talking about a few minutes ago, it's not a daily occurrence, but our terminals will occasionally lose internet connectivity. Our systems are generally designed to handle this and can survive without a connection to our corporate office, and the DNS system has to be the same way. So zero downtime deployments. Personally, I hate overnight maintenance. I think it's destructive to team morale, it gets sleep deprived, it makes you less productive, and it just adds a lot of additional planning and coordination and logistics to what otherwise would be really simple changes. So being able to change or update these systems without any downtime was probably the top requirement after the core DNS server functionality for this system. So Phoenix servers, fairly straightforward. We want to be able to burn these things down and rebuild them as quickly as possible. So we build our testing environments by taking a snapshot of our production systems, cloning it to a new set of servers, and then tweaking a couple of things, including the DNS settings. So in order for these to function as we intend, we need a DNS server that provides a subset of the functionality of our production systems, but resolves everything relevant for that terminal to the testing equivalents instead of the production instances. So this includes all of the local domains, and it also includes some, but not all of these globally resolvable domains. And then for monitoring and logging stuff, we use several different tools for monitoring, for metrics collection, log aggregation, backups, that kind of thing, all of which require installing and configuring some local components. So we want all that to be handled by Ansible playbooks. And then finally, we want a lot of testing in these systems. So more on that in a couple slides. Okay, so the architecture we actually developed to meet these requirements is pretty straightforward. First, we're keeping the central DNS server as is. There's a lot about that system that I would love to change, but it's good enough for the moment, and we don't want to add any unnecessary complications to this process. Second, we're going to set up 2 new servers at each location, running a standard bind setup on a stock Ubuntu 16.04 image. And these 2 servers are going to be identical. They're going to serve as a primary and a secondary for each, for all the systems at that terminal. And that's going to allow us to do updates and full rebuilds and all that with zero downtime. So these terminal level DNS servers will act as masters for that local zone, using zone files built and managed by Ansible. And then for the global zone, they'll act as slaves, pulling zone data from the central DNS server. And they're going to cache that data locally so that even if the terminal loses internet connectivity, global domains will still be resolvable, even though they won't be updated, of course. And then finally, we have a handful of these other internal zones that need to be forwarded to other systems, like our AD servers, and then everything else goes to OpenDNS. So when I first pitched this idea to my boss, his immediate response was, you want to add how many new servers? But he warmed up to it pretty quickly when he saw that these servers would actually be a lot easier to manage. And in addition to that, we'd actually be able to lower our resource usage because with a couple more steps, we can finally get rid of those black box servers that nobody understands. Okay, so we'll talk a little bit about the environment that this is going to happen in. And again, there's a link at the bottom there, and this is at the end of the last couple slides too. There's demo code for this in GitHub, and the demo code all runs in AWS, but it is designed to mirror the architecture of our actual systems. So everything lives in a single VPC. We have a single public subnet with a bastion host that's going to serve to run the actual playbooks themselves, and then 5 private subnets. So the central subnet, which corresponds to our corporate office here in Manhattan, where that central DNS server lives, and then 4 remote subnets corresponding to 4 different external locations, each with 3 DNS servers, 2 production ones and 1 testing server. So I've been wanting to play with Terraform for a while. Haven't really had a use case for it. This seemed like a good excuse. So there's Terraform scripts in there as well to set up all the networking components, the security groups, IAM resources, elastic IP addresses, all that kind of stuff. And then the basic setup of the 2 pre-existing servers, so the bastion host and the central DNS server. And then everything else is taken care of by Ansible. And just the requirements on that, fairly straightforward. You need an AWS account, you need the AWS command line tools, you'll need to manually set up an SSH key in AWS, and then you'll need Terraform installed. And from there, just run the Terraform scripts and then Ansible playbooks for everything else. And again, the code and the usage details, README, all that kind of stuff, is available at this website, lazza.ro/DNS. And that'll link just directly to the GitHub page. Okay, so second step, where are we starting from on this? So Ansible is going to handle most of this process, but we still need a common starting point. So we started from a standard Ubuntu 16.04 installation media. We manually configured this for the bare minimum required for Ansible to take over. Again, we do have to deal with this whole loss of connectivity thing, so most of our systems are local on physical servers that we're running, VMs on top of that. So we were actually starting from provisioning a VM, handling the installation media, and so on. So we're provisioning VMs, installing the base OS, setting up networking, creating a user account for Ansible, and setting up the SSH keys that Ansible is going to be using. Obviously on AWS, this is going to be a lot simpler. As long as you use the default user account that comes with an AMI, you can do everything else, the SSH key, the IP address, the hardware requirements and everything, all just while provisioning these EC2 instances, and we'll do that through Ansible as well. So once we've got that template in place, we can let Ansible take over. So over several projects, we've developed a pretty standard model for setting up these Ansible playbooks, including heavy use of roles to organize tasks into manageable, reusable pieces. This includes a bunch of individual roles for a lot of the general setup we do on all of our servers, so setting the hostname, installing monitoring tools, that kind of stuff. So all of these are in the demo code, but I'm going to just skip over most of them, just show a couple of the particularly interesting ones here. So we generally use the standard directory structure running in the Ansible docs, playbook and host file at the top level of the repo. We're generally using all static hosts, static inventory for these. And then in the inventory, we're using short, easy, human-readable host names, along with the Ansible host syntax to abstract away the details about how we're actually connecting to these things. So usually IP address or the domain for one of these things. And then we also have in like the group vars all file the details of which SSH keys to use and user accounts and things like that. So then we're grouping hosts into whatever logical groups are useful for us. We use a lot of the children syntax for combining groups under other groups and so on. So naturally, one use case for this is common configuration data. The set of systems and the associated domains in use is slightly different for each terminal for us. So control variables about whether a particular domain should be included, things like which vendors are in use there. That's set for, say, all of the alpha terminal servers just in the group vars file for that group. And things like the IP address of the AD servers for that location are going to be commented to that, so set there too. And then anything host specific, such as additional control variables needed for the testing servers, those are all in the host vars files. And another big use of groups here for us is stage deployments. So having servers segmented into like testing servers, production primaries, production secondaries, lets us do deployments on these low-risk servers first, like testing, and then we can proceed if there's no issues. So setting the hostname is basically the first thing we do on any of these servers. First, we're replacing the hostname file with a really simple template. And this is the same hostname that we're using in our inventory, so we can just use the inventory hostname variable for this. And then we're updating the host file, so that localhost, the hostname, the fully qualified domain name, which is just that hostname plus .global.corp, is all resolvable back to the loopback address. There's a problem with this, though. So the hostname won't actually change on this server until the server is rebooted under this setup. So to avoid having to do a reboot, we have a handler on all of these tasks that's going to temporarily change the hostname and then restart our syslog as well, so the new hostname will be reflected in the log event data immediately. And then to force these handlers to run immediately at this point in the playbook instead of at the end, we're using the flush handlers action from the meta module. Okay, so ideally management of these servers would be totally automated. You'd never have a human being SSHing into these things, but we're not quite there yet. We have a lot of situations where we might want to manually test out a change before adding to a playbook. We want to log in and just check to confirm that a config file matches what we're expecting, things like that. And this is especially true for us at the beginning of this process. So for these times, there's usually a couple of things that it's really helpful to have on hand. Packages like nmap for diagnosing network issues, or NCDU for figuring out what suddenly filled up your var partition or something like that. And this can also include things like custom bashrc and vimrc files, so that your preferred aliases are already in place when you run one of these servers. So one big thing to remember that's different with working with Phoenix servers, anything you do on these servers manually is temporary. This can be a really difficult thing to get used to, especially if Phoenix servers are a new thing for your organization. But fortunately, the message of the day system gives us a really nice way to just display a message when a user logs in, and we can use that to explicitly warn people about this. So in Ubuntu, the message of the day prompt is built from a series of scripts. So we're just replacing the standard help desk piece with a custom message here. So this is our custom script. We should probably be using tput here instead of raw ANSI codes for the text color, but it's on the list of things to come back and do on this project. So this is what the user sees when they log in. Big, scary looking, and really hard to miss. This can also be a great place to just add additional useful information, such as what this server does, where the documentation is, or even where the repo is that these Ansible scripts that manage these things live. And as we've automated more of our configuration management with Ansible, we've added similar warnings to individual files that are managed through Ansible as well. And in addition to just helping prevent these kind of changes, or at least prompting someone to say, hey, I changed this file, can you update this in the playbooks? It's also been a really useful indicator to us of just what's been migrated over to the automated processes and what hasn't. Okay, so at this point we've got all the basics in place. It's time to start turning these things into real DNS servers. So the approach we use to building new playbooks is pretty much the same for all of our Ansible projects now. We start by setting things up manually, taking notes on what we're doing at each step. Then we go back through and build out a rough playbook from these notes, testing it out at each point. We're burning down our environments frequently to make sure that it's doing what we expect it to do. And then finally we go through and we clean up and parameterize and things like that, pulling common data out, replacing similar and duplicated tasks or roles with more general stuff, plus some additional control logic. But overall though, this build-out piece is probably the least interesting part of this project. It's just setting up a normal DNS server. So you've probably either done this before, in which case you've seen it all, or you haven't done it and you probably don't particularly care about DNS servers, other than that they just work when you need them to. So rather than going into a lot of the details here, I just want to highlight a couple of the more interesting pieces. So some of the reverse engineering we had to do on these, how we handled a particular issue with the serial numbers and the zone files, some of the conditional logic we built in, and then just an interesting thing about how we did some of the reboots here. So this is probably a good time to mention that when we started this project, I didn't know a whole lot about DNS. I knew it worked conceptually, but I'd never actually built or managed a DNS server before. And you guys probably had similar situations, right? Like, hey, here's this thing that nobody on the team really knows how to do, go figure it out. So that was very much the situation for us. We didn't really know how this legacy system worked. There wasn't really any documentation, at least, that we knew of. But we did know that for the most part, these things did actually work most of the time. So given the high risk that there were probably gaps in our understanding of what was required from these systems, we decided the safest approach would just be to identify the major components that are already in place on these legacy systems, and then just use that as a starting point. So we literally just went to the legacy servers and checked what packages were installed. And that was our starting point for building these things out. So we used a similar approach for the configuration side of things, largely just compare the legacy system's configuration against the default configuration or the example configuration from whatever tools we're installing. Just combine the two of them and get them all to line up and work as expected. So in many cases, this was fairly straightforward. So we're just taking existing config files and just pulling pieces of them out into parameters. Otherwise, things stay the same. So one of the interesting problems we ran into, though, was with the serial numbers in zone files. So if you're not familiar with these, the serial number in a zone file is roughly used to indicate whether the data in a zone has changed. The specific value doesn't really matter, but anytime you change the data in here, you have to change the serial number to something that's greater than the previous value. There are a couple of different conventions on what exactly to use for these numbers. Since we had mostly managed these things by hand, the general approach we were using was just every time somebody edits one of these, you just increment the number by 1. This wasn't going to work for our new servers, though, especially since we know what the old value is if, say, we've just blown away the previous zone file in addition to the rest of this server. So the other major approach to this is to use something based on the date and time. So one of the things that Ansible is doing when it's doing its gather facts process is setting up this Ansible date time variable. And that has an epoch field in it that provides the date and time in like the Unix epoch format. And that meets all the requirements for a serial number here. It's an integer value, and it's always going to increase over time. That's usually true. There's certainly cases where it might not be true, so if we drastically change the time on a server or something like that. But for our purposes, it was good enough, and it sort of solved this problem for us.
Yeah, serial numbers, they have to be a 31-bit number, I think.
Okay.
So you might, by 2038, you might have some trouble with that.
I certainly hope by 2038 somebody else has come through and replaced these with better servers. But, yeah.
I think they're allowed to wrap to 0 though.
Yeah, we'll put it in the backlog. So as I mentioned earlier, we needed the DNS servers for our testing environments to handle the local zone normally, but we also needed all of the global domains relevant to that terminal to resolve to their testing equivalents. So this means we can't just pull in the zone data from the central server the way we're doing in production. So we did some manual testing with this, and we finally settled on having the testing DNS servers act as masters for the global zone, just using their own custom zone files the same way they're managing the local zone. So after pulling a bunch of the data out into parameters, we added an additional control variable, isIsolated, that allows us to use a single set of templates for both of these environments. So the default behavior, all the config files are set up as they would be for production. Global zone data is pulled from the central server, but any server in this testing group is going to have this control variable turned on, in which case it's going to set up the global zone. It's going to act as a master for the global zone. So this carries over to tasks as well. We're always going to deploy and validate these zone files for the local zone, but if this is an isolated server, we're also going to deploy and validate the zone files for the global zone as well. So there are several other pieces to the core DNS functionality here, but they're mostly just more of the same here. So just this approach of looking at the two different systems, combining them. This pretty much carried us most of the way through the actual build process for this. So one last thing I want to mention quickly is reboots. So our goal with these servers was to have everything be managed by Ansible. And that includes automatically upgrading whenever new packages are available. So on Ubuntu, you can do live patching of kernels without a reboot, but there's some extra work involved, and we're able to do rolling updates. We have these primary and secondary servers. It's just easier to have Ansible manage these reboots for us. But how do we know when a reboot is required here? So on Ubuntu, there's a helpful little note that's included in the message of the day prompt that indicates like, hey, this server needs to be rebooted. So we dug into the message of the day scripts, and it turns out that this is shown based on whether or not there's a particular file present, var run reboot required. So we use the stat module to check, does that file exist? We register it in a variable. And then based on the results of that, we're going to use the command module to initiate this reboot, and then the wait for connection module to just wait for the server to come back up. So this was the original approach we used. If you've already upgraded to the new Ansible 2.7 though, there is a reboot module that does this for you now.
Nice.
Though it hasn't worked 100% for us, I think there might be some pieces that we still need to figure out the exact usage of it. Okay, so that's the general process we use for building these servers. So we've got something running, we think it's working, how do we actually confirm that? So we usually think of test-driven development or behavior-driven development as really a software thing, but it can apply for server configuration too, and that's really the approach we're using here. Write the tests first, get them all to fail, and then slowly build out the functionality so that these tests start passing. So for us, this includes our standard just Nagio server checks, so disk space, load average, memory usage, that kind of thing, along with some additional DNS-specific Nagios checks, so querying at least one domain from each of the zones the server is supposed to be handling. But primarily, though, what I want to focus on here is the checks we built directly into our Ansible playbooks. I'll take you through some examples of that in a minute, but first I just want to touch on some of the guiding principles we use for this. So first up, we build tests directly into the playbooks themselves. If you're configuring a server, you're going to be running the tests for it as well. Second, the test should be narrowly tailored, so that ideally a failure of a particular test case implies a particular root cause. Third, we're going to use our environments as a testing tool. We always update our testing servers first, and then our secondary production servers, and then our primary production servers, which is really easy to do for us because we have inventory groups that cover all that. We just use the limit syntax. And then fourth, we use roles and tags to distinguish the major testing pieces from the setup and configuration pieces, so that if we want to, we can run all the tests independently. And then finally, whenever a new problem comes up, we're going to add a test to cover that situation. So since this is a DNS server, most of our functional testing is pretty simple. Just send a query to this server and then do something with the results. So this is the basic structure of our functional tests. So we're performing an NS lookup operation from within the DNS server itself. We're explicitly telling it to perform the lookup using itself as the DNS server. And for now, we only care about whether it can resolve these domains. We don't actually care about whether the results match what we expect. So if the DNS server doesn't respond, or if it responds and can't find a domain, we're going to see something like this. So this particular example is what happens when the local DNS server is configured correctly, but it hasn't been added to the allow transfer list in the bind settings on the central DNS server. So the local DNS server is going to attempt to initiate a zone transfer from the central server. The transfer will fail, and then the queries for anything in that global.corp domain, or that global.corp zone are going to fail, but everything else is still working normally. So if that internal testing succeeds, we're going to move on to external testing. So basically the same set of checks, but originating from a separate environment. In the demo code, this is actually these are being delegated to the Ansible controller. In production, we're actually using another on-site VM for this, since most of the production traffic is going to be between different systems within that local terminal network. So there are a handful of specific situations in which those previous checks will pass, but these ones will fail. So for example, if there's some network configuration that's blocking DNS traffic and blocking traffic on port 53 or something like that between these hosts, or say if bind is running, but the listen on parameter is only allowing queries from the local host. So both of those checks pass, along with a couple of others I'm skipping over. Then we come to the full resolution test. So in these tests, we're not just checking to see whether we can get a response to the query, we're also checking whether the response is correct. So as with the prior test, we're performing a basic NS lookup operation, and since we know at this point that the server is properly responding to external queries, we're just falling back to the simpler, just internal testing. This time though, we're registering the result, we're pulling the value out of the standard outlines from the results, and then we're comparing it to the test data, which is defined in a separate variable file. So this is roughly what the standard out data looks like. We're just grabbing that last line, we're removing that address prefix, and then we're just comparing that string to the string that's set in the variable file. So this is the main playbook we use for managing these servers. Originally, we started with the bind configuration and the setup piece and the testing piece as well, all in a single role. But over time, we moved the testing out into a separate role. And we added a test tag to that testing role. So this was originally just for convenience, to separate things a little bit, make them easier to read. But eventually we realized this had a lot of really useful implications. For example, we have Nagios checks that indicate high-level problems, like something, the one check in this zone is failing. It's not responding to this query. So when that happens, I can use this, this syntax to just run a comprehensive test panel against this particular affected server, or against all of the testing servers for that location, or all of our DNS servers everywhere in the company in just a couple of minutes. So finally, whenever we have a new failure occur, we're going to add a new test to cover that. So we had an example of this come up just about a month or so ago. We set up a new group of DNS servers for one location, and we realized that the clocks on all 3 of these servers were drifting by a couple of seconds each day. So after some investigation, we finally found the root cause on this. When we set up the template for this location, we accidentally left the loopback address off the list of DNS servers for them to use. So they were falling back to just using OpenDNS. And because of that, the domain name for our internal NTP server at that location wasn't resolving properly, and servers weren't able to sync their time correctly. So we realized at that point we had a hole in our test coverage. All of our tests were explicitly specifying which DNS server to use. So we actually didn't notice when the default settings were incorrect. So to address this, we added a new test to the very start of the testing role. So on the DNS server, we're using NSLOOKUP to query the local hostname without specifying which server to query. And then we confirm that the response came back from the loopback address. So similar to the full resolution tests, we're grabbing the first line now, the output from NSLOOKUP, removing that server prefix and comparing to the expected response. Okay, so all the tests are passing at this point. We have a working DNS server. Time to blow it up. So by this point, we've probably burned down these servers a couple of dozen times. And it's great to be able to do this, but the exact reasons for why we like doing it tend to change a little bit over time. So as I mentioned earlier, during the build process, we're often manually testing out changes. We're tweaking things until they're working as we want them to. And it's really easy to forget to go back and actually add those changes to the playbooks. Likewise, it's not uncommon for us to include a config file or a package or something like that, and then later realize we don't actually need this thing. I've had a couple of times when I couldn't figure out why a server was acting strangely, only to eventually realize that it was because I forgot to clean something up. I left a package installed that I was previously using for some alternate approach for something, and config files especially. So wiping out a server and performing a full rebuild, it removes these whole classes of problems, and it lets you get back to focusing on the interesting stuff here. And then after that initial process, you probably have some ongoing build and maintenance work with these servers, but the major concerns are operational at this point. So burning down these servers periodically makes it easy to practice what's hopefully a big part of your disaster recovery system, and it lets you assess how much time and effort are we going to need to bring the server back up. It's going to prevent that configuration drift. And then finally, one sort of fringe benefit, you should probably have better tools for this, but burning down a server does give you a kind of brute force way to clear out all the log data and other things like that. It's not ideal, but if you hadn't had time to set up a better solution for that, this may be a workable solution. So one thing you might be worried about at this point is how long it takes for this process. We're talking about setting up a new VM, downloading, installing, and configuring a bunch of packages, and then running a pretty sizable set of test cases. Sounds like it might take a while. And let's be honest here, if it's taking you a few hours to rebuild a server, you're not going to do it unless you absolutely have to. So on the VM side of things, how you speed this process up is probably going to depend a lot on how you're actually running your servers. So if you're in an environment like AWS, it's fairly simple to automate this process. Terminating provisioning servers with Ansible or Terraform or CloudFormation or whatever your preferred tool is. And even if this doesn't reduce the actual time it takes to do this process, if it means that you can kick this thing off, go off, do something else, and then come back to it, that may make this a feasible option. Another option that we actually use at OTG, because we're mostly on-prem stuff, you can take a snapshot immediately after you first provision one of these VMs, but before you set anything else up on it. So terminating and reprovisioning a server can take us 10 minutes. Rolling back to a snapshot takes us a few seconds. And now we're back at basically a clean starting point. And then on the configuration side, there's a couple of strategies you can use here. Some of them fairly standard. So if you're installing the same software on a large set of servers, setting up local mirrors of package repos, app yum type repos, but also things like PyPy or CPAN, whatever your particular use case is. can drastically reduce your installation time, decrease your network traffic, that kind of stuff. And then, if some of the parts of your configuration are going to change more often than others, you can set up the slowly changing pieces, bake them into a partially configured snapshot, and then, in addition to doing a full rebuild of the server, you can now do a partial rebuild. You launch a new VM from that, that snapshot, and then you can just apply the final changes in a frying step. So if you're familiar with the bake and fry terminology. And then finally, there's a few things you can do within Ansible itself to drastically speed up the time it takes to run your playbooks. So the first step in optimizing any code should be profiling. Ansible actually includes a profiling module. I didn't know this until I worked on this project, but it's disabled by default. So you can enable this by adding the profile tasks named to the list of whitelisted callback plugins in the Ansible config file. And just a note on this and all the other optimizations I'm going to mention here are included in that Ansible controller VM in the demo code. So if you haven't seen this before, with the profiling module enabled, Ansible is going to show runtimes for individual tasks. It'll show a total runtime for the whole playbook, and it'll also show a final summary of all tasks sorted by runtime. In this case, the most time-consuming step was the reboot, probably triggered by a kernel update, followed by several tasks that all involve installing new or updated packages. So together, these tasks account for almost 80% of the runtime of this playbook. So if we're looking to speed up this playbook, that is where we want to start. So once you have quantitative data, you can start playing with your Ansible settings. With these DNS servers, we found two changes that drastically improved our runtimes. And we found a third option that helped, but for some other reasons, we decided not to go with it. I'll get into that in the next slide. So the first change we did was to enable pipelining. So by default, Ansible performs these tasks by writing the module code to a temp file on the remote host, and then using a second SSH connection to actually run that code. So turning on pipelining allows it to use standard in instead of temp files to transfer that code over. So it just reduces the number of SSH calls required and can drastically speed things up. Certain settings on remote hosts can prevent this from working though, so pipelining is disabled by default. And if you're interested in the details in this, the Ansible docs have a lot more about exactly why and what the configuration settings are that can cause problems with this and all that. The second change we looked at was forks. So Ansible spawns new child processes to communicate with remote hosts, and the fork setting, which by default is set to 5, sets an upper limit on how many concurrent hosts it can operate. So Ansible won't spawn any more processes than it actually needs, though, so you can put this number up as high as you can. The only real limitation on it is just the traffic that your network can handle, and the resources available on the local machine that you're running this stuff from. These are not particularly big numbers, but I regularly run like 25, 50 hosts at a time off of this laptop, and I haven't run into any issues with this yet. And then also, the docs do include a note about this. Apparently on macOS, you can run into issues with the max number of open file descriptors. I haven't run into it, but it is something that is noted in the doc, so that may come up if you're running this on a Mac. So prior to these two changes, running this playbook on, I believe it was the secondary DNS servers for all 4 locations with this demo, it took about 13 minutes to run this playbook. These two changes alone, it brought us down to 3 minutes. So the last optimization we tried looking at was using an alternate execution strategy. So if you're not familiar with this, I actually was not familiar with this piece other than just like vaguely hearing about it until I started looking into this performance tuning stuff. So the normal behavior that most of us are probably familiar with, Ansible will complete a task on all of the hosts that you're running against, and then after it's done with all of them, it's going to move on to the next task. So that's under the default setting, the linear strategy. So under the alternate free strategy, Ansible is going to proceed to the next task for a particular host as soon as that one task is done, it's going to move on to the next task for that host without waiting for the other host to finish. So this can cut your total runtime considerably, but there are a couple of things to watch out for on this. One piece, so as usual, Ansible's output is going to show info about each task as it's completed, but the fact that different hosts can be running different tasks at the same time can make the output really hard to follow. The other piece on this, for this to work, your hosts need to be fully independent. So we have another playbook that includes a run once task that downloads a file from an artifact repository to the local controller, copies it over to each of the remote hosts, and then deletes the local copy with another run once task. And if we use the free strategy on that playbook, it'll cause the local file to be deleted when the first host gets to that step, even though it's needed for the other hosts, which are then going to fail because it can't find the file. So use a section of the output from running the playbook, running this demo playbook under this linear execution strategy. And here's the same section under the free strategy. So as you can see, it's a little bit more complicated to follow. Things are mixed up a little bit more. And this tends to get worse the more hosts you're running against, the longer your playbooks get, just because there's more room for variations and timing to come up with these things. So in practice, we did see a noticeable speed up from this. It went from about 3 minutes to about 2 minutes. So it was noticeable, but not all that big. And since we're already fairly fast at that point, we opted to just stick with the linear strategy for that. So this is the output from a full rebuild I did yesterday of the DNS server at one of our testing locations. So the template here hadn't been updated in a while. So there are a fair amount of packages that need to be updated. Plus this has a few extra pieces that I left out of the demo, including installing the tools for our backup client in particular. I don't know what it is, but these vendors' repos are really slow all the time. So that was one of the major pieces of this. But even so, the full rebuild for this server was just under 8.5 minutes. So with a time like this, I can kick this off and go grab a cup of tea, and by the time it's done brewing, my server should back up and running. So there we have it. About less than 10 minutes to blow up a server and have it rise from the ashes. So that's about it. So thank you so much for coming tonight. I hope you found this useful, or at the very least interesting. And as I mentioned before, this playbook and the slides and everything are available on GitHub, along with documentation, the Terraform scripts, all that sort of stuff for setting up this demo environment in AWS, including that control host, central DNS server, 4 subnets, and a bunch, I think, a dozen different testing and production DNS servers. So there you go. So yeah, at this point, we open up the floor to questions, and in particular, if you have comments or suggestions or ideas on how this could be made better, I would love to hear them. Yeah.
Where do you store your logs?
So that's a good question. We actually we're on, I think, our 3rd iteration of a log aggregation project right now. We are using an elk stack setup. So we have part of the setup for these. I don't think it's included in the demo, but the production versions of these playbooks, we have a step where we're installing FileBeat. We're setting up a couple of things. There's a piece in the bind configuration where we're turning on logging. We're putting all that stuff into var log named and a bunch of different files, and then we're collecting up all those files and shipping them all through Logstash instance using FileBeat. And then just Kibana for actually interacting with them. Yeah.
You talk about the life cycle. So with your Phoenix server, do you typically run this playbook just one time, or do you run it every day?
Yeah. So nowadays we don't do full rebuilds all that often. We try to, but it's the kind of thing that we'll often run that playbook once a day or once every couple days just to install the latest package updates. I mentioned before the talk started, we had a tower server, actually AWX, that we were using for a while as a proof of concept to see if it worked for us. We loved it, then we changed something, we broke it, and we never got around to fixing it again. When we had that set up though, we had these playbooks automatically running every night. So we had a lot of legacy systems. There's always a risk of if you update packages, is it going to break stuff, that kind of stuff. That was not a problem with these servers because we're always running all of the latest packages all the time on at least the testing servers, the secondary production servers. If everything goes well, we can move on to do them on production as well. So yeah, I would love to get back to that where we're automatically doing this stuff.
So I have a follow-up question then about your bind template with the serial. If you're running the same role over and over again, that the timestamp's going to change each time you execute it. How do you protect against that? Because you don't necessarily want to reload every time.
We don't. At the moment, we're changing every time. Okay. Yeah, it's difficult because if it were, say, 2 separate files, like changing the configuration somewhere, then you could do something like a handler that, if this is changed, then do this update. In practice, though, we could have changes to that zone file that are right in the same place as the serial number. One of the other things we looked at is some kind of can we have some other piece of information somewhere that's tracking the serial number, and then if something is changed, we're grabbing the latest serial number or incrementing it or something like that. In practice, it ended up being one of those things we'd probably come up with a better solution, but it's good enough. Right. So we fail a little better each time.
Yeah. No, that's cool.
Yeah.
If Do you burn down the master server? Where are you loading your zone data from?
We don't burn down the master. Yeah, so this is just covering our DNS server at each of the individual terminals. I was talking to somebody before about we actually made a change a couple months ago to fix like one guy's DNS setup on an iPad in like Philly in our remote office over our VPN. We changed one thing on that central DNS server, and it brought down our entire monitoring system because it's all running on the same server. And yeah, there's a bunch of like that's another one of our major black box servers that we eventually will hopefully replace. But yeah, to answer your question, we don't at the moment. That's sort of outside the scope of this project. Yeah.
And also, when you do the burn down and rebuild, is it a one-click operation? You just run a script once and it's done, or you still have some manual steps that you have to do?
Right. So if we want to do a full replacement of one of these servers, yeah, there are a couple of manual steps involved. With that, the approach I mentioned where we're doing the snapshots of a VM right after we set it up, in that case, it's just a one sort of, go to the web. So we use Nutanix as our hypervisor on most of our systems, and Zen on some of the others. On our Nutanix environments, it's a single button click to roll back to that snapshot, and then we can just run the playbooks against it. The Zen servers, it's a little bit more complicated, but the demo code here, it's all running on AWS. I don't know if there's actually a role that includes all these pieces, but you could very easily do a role that runs the termination script, runs the provision script, and then runs the configuration script. And that's actually how we have a lot of the other Phoenix type servers we have set up. Yeah.
Just a suggestion, one time when I had to manage and build Hadoop clusters over and over again was, I wrote a playbook that could, if you told it you're going to rebuild, it would zero out the MBR and then restart, and then PixieBoot would pick it up and reinstall like everything out of PixieBoot. So just, I don't know how well that would work with a VM system, but that's something I tried. So
very cool. Yeah. All right.
Was there any advantage to using Ansible pull for any of the kickstart the actual booting process? Is that something you looked into, or was that not useful?
Yeah, I actually have not looked into that. I've read a little bit about it, but yeah, just haven't had a chance to look into it. But no, that is definitely something that I would like to look at on this, but haven't gotten a chance to yet. Yeah.
I just used it in the past just to have like an isolated build, just right from the boot process to stand the whole thing up from scratch. Yeah.
Okay.
Curious.
Yeah, we'll definitely look at that. Yeah, thank you.
So you kept saying that you want to have zero downtime, but for the DNS client's point of I guess from the DNS client's point of view, if it's depending on how it's set up, it may not may wait 15 seconds before retrying. So what actually happens when you have a server down?
Yeah, so if we have one of them down, yeah, it's something along those lines. So I think this is one of those, I don't really know a lot of the details on this on the DNS server side. But yeah, I believe what we have happen in those situations is exactly that. There's some kind of a wait period in which the client realizes like, hey, this server isn't responding, I'm going to go over this. So there's probably some amount of lag in there. So far, we tend to use the screen test for a lot of these things, take down the primary and see if anybody complains about it. In practice, it has not come up yet, so at least it's good enough for our current use case, it seems like. Yeah.
So the clients are all iPads?
So iPads primarily, we do have a couple of other systems. We use Mac Minis and Raspberry Pis to make sure they're both, to actually do coordination with some of the other hardware, like the card swipers. And again, yeah, those are configured the same way, so with the primary and the secondary both listed as DNS servers.
But have you looked at the resolve conf and how long they wait and how many times they retry? Have you tuned those?
We have not. I believe all of the DNS settings are actually coming from DHCP for a lot of these things. But yeah, that is definitely something that we should look at some more. Yeah.
Depending on, especially you're going to move to Raspberry Pis, like using DNS Mask allows you to do things like it can keep track of which DNS server is actually available and update that kind of stuff like dynamically. So. Something to consider.
DNS Mask will do
that? I think so. I'm pretty certain. I believe it's like a configuration setting. I was playing around with it with Consul, like using Consul to replace our DNS servers, and there was like something about that. And I feel like maybe systemd too is also doing some stuff with DNS that might be helpful in this situation, especially again if you're using like you move to 1804 for instance, and you get like systemd. You do get some nice new things around like DNS and stuff.
That was another big part of this project. We moved from Debian 6 on the oldest stuff, or Debian 7 primarily on most of our servers, to Ubuntu on this. So yeah, one of the big changes there was systemd. So that was another interesting part of this project that came up. It was the first time we did a lot of
I feel like it was systemd with DNS Mask where I discovered that you can sort of track or keep track of the DNS servers upstream or something like that. It's all vague. I didn't play with it that much. It kind of makes sense if you think about it. That'd be a nice thing to have, since yeah, just because the typical default timeout is what, like 15 seconds or something. So if you can remember that, hey, this one didn't work 15 seconds ago, I'm not going to try it again on the very next request. I'll wait, 1 minute and then try it again or something like that.
No, 1 minute's a long time for the client.
No, I just meant, like, don't try that DNS server for another minute.
Oh, I see, all the subsequent queries
Yeah,
go to the working server,
yeah.
and then you go back and check, yes.
Yeah, I had some issues in the past dealing with Linux servers resolving by 9, failing over from primary to secondary. Oftentimes they wouldn't fail over. We didn't know why. Are you using load balancers anywhere in there to just eliminate the need to fail over to use the resolve.conf? Just go straight to the load balancer and have that figure out?
So we aren't currently. We're actually going through a process of really pulling apart what are really like monolithic systems into more microservices-based stuff. I've got a list of like a dozen different things that we need to start looking at load balancers on. This is definitely one of them. But yeah, at the moment, all we're doing is the primary and secondary.
So in your resolve.conf, you can set the timeout much lower, to like 1 second, for instance. So
I had strange issues on CentOS where for some reason it just wasn't failing over, or it was taking a while to fail over when the primary was.
I definitely recommend reading the man page. There's some hidden gems in there as far as configuration options when it comes to the resolve.conf and stuff like that. So yeah.
Yeah, it's options for rotating lists.
Yeah.
You can go round robining or how long the retry timeout's going to be.
And I think how many retries you can do and stuff like that before it fails.
That too.
So you're talking about frying and baking. So what was the logic? I don't know if you thought about it. Why not have fully baked golden image and just bring that up whenever you need it?
Yeah, so this is a good question. One of the big challenges for us is if we create one of these templates, moving it around. A lot of our locations are geographically fairly distant. The network links aren't great between a lot of them. So it ended up just being easier for us to do a manual one-time setup process of a basic Ubuntu template at each location and then just have everything else get taken care of rather than, say, setting up one template, getting it fairly far through the process, and then cloning it to all of our other environments. So yeah, it really just came down to like this is sort of a faster thing to get us to this point initially. It's definitely one of the things on the list though that we want to look at, especially as we're also in the process of transitioning from using Zen everywhere to using Nutanix everywhere. So we have this whole thing with different systems that use things work slightly differently between the VMs on them. So at the very least, we need to maintain 2 different images for that stuff. But yeah, as we get more standardized on a lot of this, that's definitely something we're going to come back to looking at.
Another comment, we use Consul DNS, so we don't run like dedicated DNS servers.
Okay.
Yeah.
Instead, Consul DNS, it performs like application health check,
Yeah.
and if that application is up, that specific server that serves that application is up, then it's in the DNS round robin. If it's down, then it gets removed from it.
Yeah, and Consul has a concept of federation within. So you can basically say, look up my local version of this, or look up the version in another data center, or look up the global one. So it would actually map into your multi-DNS domains, I think, or your multiple domain thing pretty well.
Yeah. Awesome. Thank you. We'll definitely look into that. Yeah.
So you mentioned you used to use Tower or AWX before and stopped using it?
Yeah, so we started using it. We loved it. We initially set it up all on one machine though. I think it was like 3 different containers running on one system. We went to move the database piece of it. We pulled up the database to another server. We went through and changed what we think we needed to change for the configuration, and it just wouldn't start up. Even moving it back, it wouldn't work. So it ended up getting put on the list of things of like, we really like this, we definitely want to come back to it, but we just haven't had time to come back to it. So yeah, it's definitely on the list of things we want to do. But yeah, I loved using it, and it's actually, we are trying to transition to a much more like self-service model, and we probably, if we don't get an actual orchestration system up by then, we probably will end up using it as the basis for allowing developers to do self-service deployments of containers to like test environments.
So one more advanced features in AWX, I don't know if are you at all familiar with the isolated nodes in Tower, which allows you to run playbooks against hosts in different VPCs if they only have a private IP.
I'm not familiar with that. I would definitely look at that, but yeah.
I wonder how you solve that problem if you have multiple VPCs and hosts in different VPCs that have private IP addresses, any one of them your playbook against those hosts. Do you have a server in each VPC?
That's a good question. So I believe, so we have a fairly limited amount of stuff that's actually in AWS in terms of like actual VPCs. Most of the rest of our networks are, I think we have like a NAT set up at 1 or 2 of our locations, but for the most part, I think everything we're doing containerized is all on a single sort of globally accessible set of addresses and all that. So yeah, so we have the other sort of problem of like making sure things don't accidentally talk to each other when they're not supposed to be. But yeah, I don't think for a particular use case that's come up yet, but it may. Yeah. Yes.
I think you mentioned the problem with the resolving DNS names with the primary and secondary DNS.
Mm-hmm.
I don't think there's too much to figure out from the server end to control that failover if it exists. That's mostly handled from the client's resolver library.
Right, okay.
What you can do is set up an anycast address on your local network and configure your DNS servers to resolve from that anycast address. Whenever query traffic gets sent to that anycast address, the routers on the network will send the request to all the servers configured, and the fastest server that responds will get its response sent to the client. So that way you have built-in failover. It's all done at the network level.
That's awesome. We'll definitely look into that. Thank you. Yeah.
Last question.
Yeah.
Do you use any other frameworks for infrastructure testing? To test the actual infrastructure. You mentioned that you are using Ansible to test some of the infrastructure configuration. Are you using anything else?
For testing? That's a good question. I don't think so yet. Yeah, and testing is another area where we're actively trying to make a lot of improvements. I think so far it's just so Ansible and then just like Nagios checks kind of stuff, but that's more on server behavior rather than infrastructure. We've also started doing a lot more in terms of like metrics collection and like some level of like alerting around that too. But yeah, in terms of testing, I think it's just Ansible at the moment. Yeah.
I definitely recommend server spec or RSpec, depending on sort of your use cases. The nice thing about server spec is you can sort of do things like test 2 things talking to each other that you're not necessarily, like, it doesn't have to be on your control machine. You could like set up a test to like, go and talk to this other node over here, for instance, right? So, and there's some other new stuff. We're using AWS spec, but I guess that wouldn't necessarily help you guys. But yeah, a lot of new stuff.
All right. Well, just to wrap things up finally. Call for speakers. This is actually my first time giving one of these talks. I totally never thought this is the kind of thing I would do until kind of talked me into looking into it. If you have a project that you've worked on that you think is interesting, there's probably other people here who think it was interesting too. If you've run into issues with Ansible and solved them, like I would personally love to hear that, and I'm guessing a lot of other people would too. So consider giving a talk. Yeah. All right. Well, thank you everybody for coming.
I want to thank Amy from RapidSOS again for helping us coordinate all of this. So I hope everyone has a great evening. If you want to mill around for a little bit, it'd be great to talk, but keep in mind, like, people work here and I'm going to get home, so it's not a party all night, guys. But thanks again for coming out. Thank you.
Thank you.